number of points, more than or equal to 5.
Okay. So, okay, it is now 3 minutes after, and we're at the place where we stopped last time. And now it's now for the final lecture, regrettably, since we came to enjoy it so much of this mini course by Edward and Pavel, I turn it over to Pavel.
Okay, thank you very much. And today I will speak about, so last time we talked about this analytic approach to the Langlands correspondence from our joint work with Edward Frenkel and David Kashdan, and in particular about Hecke operators and differential operators, commuting with them, and the spectral theory and all these things. But in a special case of genus 0 projective line with 4 parabolic points. So today I will consider the case still of genus 0, but in the group SL2 or PGL2. Actually, G is PGL2. The Langlands dual group G check is SL2. I will still continue to assume that that it is PGL2 and that genus is 0. This is the only case when we have a more or less complete theory. And but I will consider the case of larger number of points. So so the number of points will be called n, and it will be little m plus 2. So it was convenient to put one of the points. So these are points on projective line, and it will be convenient to put one of the points at 0 and the other point at infinity, t0 and tm plus 1. And then there will be m points t1 through tm. So this is why I introduced this number m. And the dimension, so we have this moduli space of PGL2 bundles with parabolic structures at those points. So basically, this means that at every point I choose a point in P1. So I have P1 to the m plus 2 modular SL2. And this is an m minus 1 dimensional variety. And it has 2 components, even degree and odd degree, which are in fact isomorphic. And there are many ways in which they are isomorphic. In fact, if we pick any of the parabolic points, we have this involution Si, which exchanges these components. And it is just the Hecke modification at the corresponding point, Ti, along the fixed line at that point. So these Si satisfy the following relations. The Si square is 1, and they also commute. So there are m plus 2 of them. So we can use one of them, and it will be S infinity, the one that corresponds to Sm plus 1 corresponding to infinity, to identify these 2 varieties. And then the other ones become automorphisms of a single component. So I can compose it with this identification. And this will give me an action of the Z mod 2 to the m plus 2 sub 0 on this component. I mean, I can, without identification, I can also say that. I will just take an even number of generators, and that will map every component to itself. So that forms this group, which is a subgroup of Z2 to the m plus 2 of elements with the sum of coordinates being 0. And so that acts here. And we had that action before for 4 points. So in that case, we had action of Z mod 2 to the 4th 0, which is Z mod 2 to the 3rd group of order 8. But actually, it was a group of order 4. So because in the case of 4 points, there is an accident. And one of those maps, namely the product of S. So in that case, we have S0, S1, and S2. And the S2 happens to be equal to S0, S1. So the S0, S1, S2 happens to be the identity. That's an accident for 4 points. And for high number of points, that doesn't occur. Okay, so, but in any case, as before, our bundle is going to be trivial as an abstract bundle. So it's all plus O. And I view it as a rank 2 vector bundle, but regarded modular tensoring with line bundles. And this will be a degree 0 bundle. So it's O plus O. And parabolic structures. So again, we're considering stable bundles only. And so generically, it's going to be like this. And everything is birational here because we're doing integration. So I can just take trivial bundle. And then parabolic structures are just points on P1 that I have to assign at each point. And at the point 0, I assign vector 1, 0. So I represent points on P1 by pairs of numbers. So at 0, I have 1, 0, then y, y1, y, y2 up to y, ym at the point tm, and 0, 1 at the point tm plus 1, which is infinity. And y1 through ym are numbers in our ground field f, which is a local field. So it could be real or complex or could be a p-adic field. And then, well, this representation is not bijective because we can scale these y's. And this doesn't change our bundle, because if we fix things at 0 and infinity, we still have a residual symmetry, which is a scaling. So so that means that we have this symmetry, and therefore we identify band 0 stable with P m minus 1. Well, not quite, because it doesn't mean that it's literally that, but birationally it is so. In fact, it turns out that this band 0s is some kind of blow up of this P m minus 1. And for integration theory, it doesn't matter what precise structure it has, although it does matter if you want to really understand things. So any questions up to this point? Andrea, is the speed okay?
Yes, Pasha, it's okay.
Okay. Okay, so then, so Hecke modification, again, so it is similar to what we did last time. We had a formula for it. So we have this bundle E sub y, which is attached to vector y1 through ym. And Hecke modification of that will be bundle E sub z. And then the proposition is that z is expressed in terms of y by this very nice formula. Zi equals to x times yi minus s times ti over yi minus s. So where y and z are like here. And this allows us to write down explicitly the Hecke operator. So Hecke operator, as you remember, is attached to a point. Is we have to integrate over all ways to do a Hecke modification at this point. And so H is going to be the Hilbert space. So it will be half densities on this projective space, which is the same. We can think of half densities on projective space. So what is half density? The sections of square root of the canonical bundle, essentially, or absolute value of canonical bundle. So canonical bundle has degree minus m. So we can have, we can say that these are functions on f to the m, which are homogeneous of degree minus m over 2. And what kind of functions? Well, they're so homogeneous means that they satisfy this condition here, where lambda is a number in our ground field, and also that they have to be in L2, not as a functions here, but as half densities here. And another way to think about this space is we can kind of restore one more symmetry. So we assume that T0 equals 0, but we can forget that condition and just have T0 to be anything, and also Y0, the parabolic line there, to be anything. Then we will have a symmetry not just by dilations, but also by translations. And so then we will get a space of functions on f to the m plus 1 with coordinates y0 through ym, and they are translation invariant and homogeneous of degree minus m over 2. And so this is actually it's going to Hecke operator will look even nicer if you write it in this setting. And so this is for parabolic points t0, t1 up to tm and infinity. And then the Hecke operator, well, I will consider modified Hecke operator, which is renormalized by some product of norm of x minus ti to the 1/2. And I remind you, this norm is the norm of the local field. So for real numbers, it's absolute value. For complex numbers, it's square of the absolute value. And for p-adic, it is the usual norm. And this is the main formula for Hecke operator. So Hecke operator of a function psi of y, which is a function on which is a half density. So it's a function of y0 through ym, which is translation invariant and homogeneous of degree minus m/2, equals the integral over f of this function applied to points t0 minus x over s minus y0, and so on, up to tm minus x over s minus ym, and against the measure, which is the norm of ds divided by product from I equals 0 to m of s minus yi. So that's the formula for the Hecke operator. So any questions up to here? Okay, speed is fine. Okay.
Fantastic, fantastic.
Okay, so now we want to do spectral theories. So we want to show that this operator is a good operator in L2, which means it is bounded and moreover compact. And then we will be able to use, also we want to see that it is self-adjoint. That will be easy once we know that it is bounded. And then we will take its eigenvalues, and that will give us the desired spectral theory. So how to show that it is bounded? So here is this first theorem. It's not obvious immediately that it is bounded because it's given by some kind of integral, and this, integrand has, well, it's integration over some subset of the square of my manifold, and also the integrating against some measure which has some poles. So you really have to show that it is bounded. And so how? But it turns out to be easy. So in this case, so. Well, for this purpose, it's better to kill all the symmetry. So that means that we are taking t0 equal to 0 and tm equal to 1, and also y0 equal to 0 and ym equal to 1. And then we will have a function psi of 0, w1 through wm minus 1 up to 1. So this is a function of m minus 1 variables. We think of it, so we have this projective space of dimension m minus 1. And we think of function on the big cell of this projective space. And then the norm, L2 norm, is just, you can check that that's just the usual L2 norm with respect integral of over fm minus 1 of absolute value of phi squared dv, where this is the usual Lebesgue measure. And then you can write the Hecke operator in the following way. So first of all, we have this operator, which I call uxs of phi. And this is simply, it acts on half densities, and it simply does this change of variables. So if you write Hecke modification without this killing all the symmetries, remember we had this quadratic map. And so here we have it with respect to every variable, ti minus s minus y, ui minus, so ti s minus ui x times s minus 1 over s minus ui s minus x. And we have to apply it to every variable. And of course, so any, so if you have a space of half density, so any variety, if you have a birational transformation of this variety, it acts as a unitary operator on L2 of this variety, where by L2, I mean the space of square integral half densities. And it acts exactly like that. So this factor is exactly because it's a half density. So it transforms by multiplying by the square root of the Jacobian. So that's a unitary operator corresponding to a birational transformation. And then it turns out that this hx is just the integral of this unitary operator corresponding to point S against a measure which, well, this is just a constant because X is fixed, but the measure is 1 over the square root of the norm of S, S minus 1, S minus X, ds. So, and therefore, because it's a unitary operator, we can estimate the norm in this stupid way just by taking absolute value under the integral. So absolute value of unitary operator is 1. And so the integral norm of hx is estimated as less than or equal to integral of this expression, which is basically, it's an elliptic integral actually. And so it's convergent because at all the points where it has singularity, it has a square root singularity, and that singularity is still L1. And so that means that this operator is bounded and also it's self-adjoint. So that's easy to see from this formula because you can just take formal dual and you will see that the simple change of variable in S transforms that to the original integral. And also these operators pairwise commute simply because Hecke modifications at different points commute because they can be done independently and it doesn't matter in what order you do so. So any questions up to this point? So questions?
So far, so good. Go ahead.
Okay. Now, but we want to know that this operator is also compact. And this question is a little bit more subtle. And the reason is the following, that, well, remember when we had 4 points, what we did is we first tried to take, to show that this operator was Hilbert-Schmidt. And Hilbert-Schmidt is a property that you can check easily from the kernel. Namely, you take the integral of the square of the kernel, and that's supposed to be finite. But that turned out to be not so. It turned out that that integral was logarithmically divergent. So we actually had to take a square of the operator, and that was Hilbert-Schmidt. But here, well, there at least we had a chance because we had the kernel, which was a function on the square of our manifold, in that case P1, and we took the square of this function and tried to integrate it. Then we failed because the integral was logarithmically divergent. Here we cannot even get started this way because our function, the kernel, the Schwarz kernel of this operator is not a function, it's a distribution, it's a generalized function. So our variety is of dimension m minus 1, and so the square of the variety has dimension 2m minus 2, but the distribution lives on a subvariety of dimension m. So because this operator is given just by one integration with respect to s instead of m minus 1 integrations. So it has no chance of being a Hilbert-Schmidt operator. And in fact, even if we square it for large m, it will not be Hilbert-Schmidt. So square will be supported, it will have 2 integrations, so will be supported on variety of dimension of bundle, bun plus 2, and then if you take cube, it will be dimension of 1 plus 3. So we will have to take at least m minus 1th power for it to be Hilbert-Schmidt. And so it turns out that there is no, if you're given kernel by an integral of this sort, there is no simple criterion for the operator to be compact. But so it's still the best proof, the best strategy of proof is to take a power of this operator, big enough power so that it is Hilbert-Schmidt, and then show that it is Hilbert-Schmidt, deduce that it is compact, and then say that if you have a bounded operator whose power is compact, then the operator itself is also compact. And that follows from, well, for self-adjoint operators, which follows from standard theorems in basic functional analysis, basically from the Hilbert-Schmidt decomposition. And that's exactly the strategy that we used. So, and it turns out that this can be done using some very basic representation theory of the group SL2 over local field. So So what it suffices to check is that hx to the n is compact operator for sufficiently big n. So for this purpose, I look at this measure, d nu x of s, which is the measure we already used. This is the measure I have to integrate my unitary operator against in order to get hx. And so then hx to the n is integral over f to the n of u s1x up to u snx. It's a product, non-commutative product in general. D nu x of s1, so on, d nu x of sn. So, but these things should be thought of as elements of the group SL2, depending on S. Remember, this is so what is USX? I mean, it's an operator, but I'm kind of abusing notation, and I denote by the same letter just this transformation. So if you look at this transformation, so this is think about this as a function of U. So this is a fractional linear transformation of U for fixed t, x, and s. Well, t and x are fixed, but s is varying. But for fixed s, it's a fractional linear transformation of U. So this is an element of the group SL2F, or maybe PGL2F, because we are acting by projective transformations. And so I can think of this element as lying in PGL2 of m-1, because I'm doing it in every coordinate. And in every coordinate, I have its own t and its own, well, x is the same for all, and s is also the same for all, but t is individual for each coordinate. So I have, so this is an element of this power, PGL2 to the power m-1. So now, well, I'm integrating over f to the n, but I want to rewrite this as an integral over my group, PGL2 to the m-1. So I have my map, affine space an to PGL2 to the m-1, and this map assigns to s1 through sn the product of those matrices us1x, usnx in PGL2 to the m-1. But now what I can do is I can take this measure and I can integrate over the fiber of this map. So it turns out that this well, for small n, this map is not dominant because n is too small. So n has to be at least 3m-3 for this map to be dominant. And it turns out it's easy to show that once the dimension allows it, this map is dominant. So it's basically a finite cover, branched cover, but doesn't matter because we're working birationally. And then we can simply take the direct image under this cover of the tensor power of my measure, nu x to the n. And this will be a measure here on PGL2 m-1 of f. It will be a measure with finite volume. And direct image here just means that I'm going to add up things over the fiber, because fiber is finite for this map. So this is what I'll do. And so this d lambda is therefore equal to some L1 function, fx of g times dg, where dg is the Haar measure on this locally compact group. And now, so we're acting on half densities. And so we should consider the principal series representation of PGL2F on half densities on P1 and take m-1's power. It's a unitary representation of this group. And then hx to the n is simply the action in this unitary representation of this function fx of g, or rather of this measure fx of g times dg. So it's given by this formula, where rho of g is my unitary representation. And now we will use the Horizontal theorem. In fact, a very baby case of this theorem, which is trivial, basically trivial. And it says that if you have a group like this, like a p-adic group, the group over local field, and you have a smooth function with compact support on this group, which in the complex and real case means the usual thing, but in p-adic case, it just means it's a locally constant function with compact support. And if you integrate the operator rho of G, action operator, against this function, you get a trace class operator, in particular compact. In fact, there is a very simple formula for the trace of this operator, which is simply, this is basically the theorem of existence of character of this representation. So if you take, so the theorem says that if you take an irreducible unitary representation, then such a thing exists. And in fact, in the case of W representation on half densities, you can compute this completely explicitly, and it's very easy to see that this operator is trace class. In fact, it's given by a continuous and even smooth kernel, and so it's completely trivial fact. And so in particular, this operator is compact. But now, okay, so this is not quite what we need, because this fx of g is not a smooth function. It's just an L1 function. But it can be L1 approximated by smooth functions with compact support. And therefore, this hx to the n can be approximated by compact operators in operator norm. And therefore, it is itself compact, although it may not be trace class, but it is compact because it's a limit of a sequence of compact of trace class operators. Okay, any questions? Questions? So is it too fast?
Can I ask questions? So basically, are we trying to understand, what are we trying to understand right now? We're understanding the compactness of the operators, but
yeah, that's right. So we have to establish, we want to establish spectral theory. And for this purpose, we need to know that this is a compact operator, that it has discrete spectrum.
Okay.
And so bounded means it already has a spectrum, but to show that it has discrete spectrum, we need to know that it is compact. And this is what I did. Does it answer your question?
Yes, makes sense. Yeah, thanks.
Okay, so so now everything is good. So we have done the analysis and we can kind of reap the benefits. So we have this nice family of operators, hx. How does it behave when x goes to infinity? So we discussed that for 4 points, and the answer is exactly the same here. So it behaves, for example, when x goes to infinity as just a scalar times some function, which is norm of x inverse times log of norm of x. And there is a similar asymptotics at the point ti. There is no norm of x because, okay, this is a hx is a half minus 1/2 density, but we identified it with functions by multiplying by some kind of product of ti minus x to the 1/2. And so that's why you don't have this factor. But actually, it behaves exactly the same way at all of the points, except that it will have these si factors, which are these involutions at the ith point. And at the infinity point, there is no si because we have used it to identify the components, and so it's just missing. But otherwise, it's exactly the same. And so we have a spectral decomposition into eigenspaces of hk, fhx. So hx psi equals to some function beta of k of x times psi. And this chi k, to characterize the asymptotics of these functions, beta k of x, we'll decompose. So remember, we have this group which acts by unitary operator on our unitary operators on our space, and it commutes with all the hx's. So in particular, we can decompose everything into sectors with respect to this group. So chi k eigenspace, and then so that means that on each of those eigenspaces we have a particular character chi k, and then beta k of x is log of norm x, basically inverse times this character of the SI when x goes to TI. So this is the asymptotics. And this is what it is at, so beta k of x is actually positive near x goes to infinity. So this is really, infinity is distinguished because we used infinity to identify things. And what are the properties of this operator? So for example, so it has eigenvalues, and the question is how fast they decay. So they actually decay as a power, but what power we don't know precisely, but we have a guess. Well, the theorem is that for large enough A, if you take absolute value of this operator to the A, then this is trace class. So in particular, this means that this operator hx to the A over 2 is Hilbert-Schmidt. And
but I apologize. I discovered I was muted the whole time, so I actually had a question.
Ah, yes, you were muted.
Yeah, I was muted the whole time. So can we see the operator again?
Yes. So this is okay. So okay.
This operator.
Basically, this is all the formulas are now on the screen. Yes.
Yeah. So suppose are you proving some fact of the following nature? Suppose you have an operator which is like an integral of a unitary operator.
Yes.
And in one variable, it's compact. And now you're doing like you take the tensor product of these unitary operators, and then you integrate again, still a single integral. You're doing the same change of variable in all variables. It's like the tensor product of tensor u.
Not the same, because there is a t here. So there is a t1 here, for example, and here it's tm minus 1. So I'm doing different, slightly different change.
Well, is it not amounts to shift of s? Is that?
No. Because here, see there is a ts, and here is just s.
Okay, suppose you have a collection of operators for which you all know they're compact, and they're somehow. Then you take not the integral. You have an operator in the ith factor, depending on the variable of s, and then you know this integrals with whatever t it is, the integrals compact over that just direction. And now you're integrating this u1 tensor u2 tensor u whatever n. This is not necessarily compact. This is this would be there's some examples where this is not.
So I'm okay. So the formula that I get is this is the formula. So I take the power.
Mm-hmm.
Yeah. So I could not show directly that the operator was compact. Yes, I could not directly show that it was compact. So I took a power. And the power is this so it's not a tensor product, it's a composition.
No, but in your original operator, that was just a tensor product of things, right? There was one change of variable in each coordinate, and then you integrate once.
That's right. Yes.
And so you would imagine if that operator had some spectrum which the eigenvalues sufficiently oscillate, that integral would make all of them compact, right? Suppose you have a u tensor u tensor u tensor u tensor u that has some decomposition in which maybe the eigenvalues eigenfactors oscillate sufficiently fast, and then you integrate, and so that smooths out the eigenvalues.
Yeah, so you need to so somehow this curve along which you integrate has to be sufficiently non-degenerate for that. So that you have cancellation.
I thought if you integrate rapidly oscillating function anyhow, that it's gonna get cancellation. Well, anyway, sorry. All I meant to say is that maybe there's some general theorem to that effect that reduces for not this specific operator, but not some general operator of that form that reduce.
I mean, it's basically this is what is done here. So what? But yeah, I'm working on this group. So I have some curve on this group, right? And then I integrate along this curve. So, and what I'm doing is I take a convolution of this thing with itself many times. So I convolve this curve or distribution that lives on this curve with itself many times. And if the curve is sufficiently non-degenerate, then when you do it the number of times equal to the dimension of this group, you will get something that is nice, supported on the whole group and L1 function. So this is what I mean by saying that to get good cancellation, you have to, this curve has to be sufficiently non-degenerate. In other words, what's important is that this map is a dominant map as soon as this n equals to the dimension of this group. But if
maybe, what I was proposing is something else. Suppose you already have tensor product of operators and you have spectral decomposition for that. All you need to show is some cancellation between that, you know, some large eigenvalues are small, and the way to do it is to you integrate some function, and that if that function oscillates sufficiently rapidly, that this would be a small number.
Well, I don't know how to make that work.
Okay. All right. Sorry for slowing you down. Please.
No, that's okay. Maybe we should discuss this more. But I couldn't make this work. In fact, I don't know any proof of compactness of this operator which is not based on raising it to a power. So.
Well, I obviously don't know either. So.
Yes. But it is, I agree that it would be interesting to know whether this is true. But I don't think it's true that if you take any integral with respect to one variable of such product, it will necessarily be a compact operator. For example, you could take a tensor product of some, suppose you have some integral on a one-dimensional manifold, which will be compact operator, and you tensor it with the identity. So tensor product of a compact operator with the identity is not compact. But identity.
No, but you see, you have a spectrum in each variable, and in each variable, the spectrum is, you know, there's some. If you go further and further in the spectrum, this becomes get more and more oscillating. So if you're integrating enough, then this would be. Well, anyway, we can talk more about it.
So probably you're suggesting in some way that to use the fact that this curve is sufficiently non-degenerate, which is exactly what's used in this argument. So maybe you can check that if the curve is sufficiently non-degenerate, this operator is compact without raising it to power. So this statement will be true for any curve in this group, which has this property that if you take a product of, you know, define this map, basically for any curve that generates, whose image generates this group. That's true for any curve when image generates this group. So that's all you have to check, which is pretty easy actually.
Great.
Mm-hmm. Okay, so for large A, this is a Hilbert-Schmidt operator, but it can't happen any earlier than dimension, because if I take hx to the A, its kernel, okay, for this to be Hilbert-Schmidt, I need, so I need this, the kernel of this operator to be L1 on the, I mean, sorry, I need the kernel of this operator to have full support. And so that means that A over 2 should be at least the dimension, which is m minus 1. So and in fact, you can show that for any smaller A, not even an integer, this is not a trace class operator. And even, so for this one, for this A, it was not also trace class, it was logarithmically divergent. But I expect that actually if A is strictly bigger than this, it will always converge. In other words, if I define the, so to speak, zeta function, which is a trace as a function of A, then the first pole will occur here. So, but I haven't shown this one except in the, basically in the 4-point case. Okay, so now I will talk about the case of Archimedean fields, so over real complex numbers. So this is closer to mathematical physics. And in this case, besides those Hecke operators, we have this Godin system, which is the in genus 0 in GL2 is a Hitchin system. and a quantum Hitchin system. And the Hamiltonians of this Godin system look as follows. So remember, we have these coordinates yi, and this is second order differential operators, which has this form. I call this gi tilde because I actually will need to subtract from them some constants. This is a very minor point. But the properties of them as follows: they commute. Their sum is 0. So this is, they act on functions with the symmetries that as I said, which means translation invariant, homogeneous. So the sum of them, so the m+1 operators, so they're labeled by index from 0 to m, and they commute. Their sum is 0. They are formally self-adjoint, formally symmetric, and the sum of ti times gi hat equals to m/4. So because of these two equations, they're in fact only m-1 operators, which are independent, and they form a quantum integrable system. So the theorem is the following. So how are they related to Hecke operators? So this theorem is called the universal Oper equation. And it is says that Hecke operators satisfy a second order linear differential equation with respect to x, whose coefficients are these Godin operators. And from this will follow that they also, these Godin operators, commute with Hecke operators. So this equation has the form. So we have this dx squared plus the sum g greater or equal 0. Actually, it should be I. So I'm going to use this I greater or equal to 0. X minus 1 over x minus ti times dx. So this is a kind of expression, universal expression. Doesn't depend on anything. Applied to h. And this is equal to h times the sum of gi divided by x minus ti. So again, this needs to be understood in some analytic way. So it's not just an algebraic. Well, I mean, this can be thought of as just an equation on the kernel, and this way it can be checked. But then you have to show that it's satisfied in a little bit stronger sense. So I talked a little bit about that last time. And from this you can derive, if you have a slightly stronger analytic version of that, you can show that the operator gi acts by a scalar mu ik on the eigenspace hk of our Hecke operators, and in particular, and also that, of course, as a result, gi commutes with the Hecke operators. And then you can, this universal Oper equation can be specialized to get an equation for the eigenvalues beta k of x of our Hecke operators. So they will satisfy the ordinary Oper equation, which is this Fuchsian differential equation here. And so what is this thing? So, for example, over complex numbers, this beta k of x is just a real analytic single-valued solution of this equation. So it doesn't have complex analytic single-valued solutions, but it has real analytic single-valued solutions. And it will also satisfy a similar, this is a real function, so it will satisfy also the complex conjugate equation. And so in particular,
that looks like a very overdetermined system, since you have an asymptotics on this big case.
No, this is a equation with regular singularities. So
right, but since you already have the asymptotics on big case, that's like a looks like an equation of on your mu I case, right?
Yes, and it turns out that in fact so in the real case, for example, that will impose some restrictions on mu I case. because we want to get a discrete spectrum for mu case, and that's exactly what will determine the spectrum. So for complex case, you can introduce a condition that this opera is a real opera, as in the talk Edward Frenkel in my previous talk, which means that its monodromy lies in SL2R, and that turned out to coincide with the condition that you have a solution with asymptotics as specified.
Oh, okay.
It's not obvious, but it is true that there are two. I mean, one condition is that it's a real opera. Another condition that you have these asymptotics, and they turn out to cut out the same set. Does it answer your question?
Yes, yes, it does.
Okay, so then Hecke operators have a joint simple spectrum. So why is it simple spectrum? Because if you have, so it is known so that monodromy representation of an opera is always irreducible. So if you have a single valued eigenfunction like this, which corresponds to a Hermitian form on the space of solutions, the invariant Hermitian form, this is always unique. By the way, it's an indefinite Hermitian form, as I mentioned last time. It has signature 1, 1. But it's unique up to scaling, so this thing is unique. And also, oh, sorry, this has to do with the fact that no, this is not just that. It's the Hitchin system, quantum Hitchin system, also has monodromy, and it is known that this monodromy is irreducible. This is actually a deep result of Dennis Gatesbury, and although for SL2 maybe there is a simpler proof, but it's irreducible, and therefore the eigenfunction is unique and up to scaling. And also, if you look at the set of real operas, which are operas with real monodromy in SL2R, then for every mu in there is a unique up to scaling analytic half density defined out on the moduli space of bundles, which is defined outside not very stable divisor. So what is not very stable divisor? So we have this band 0. And not very stable divisor is bundles which do not have a nilpotent Higgs field with appropriate behavior at the parabolic points. So it's actually a rather complicated divisor, and I will describe it in an example. And this divisor is, well, I mean, in terms of my lecture, the easiest way to define this divisor, it is the divisor of singularities of the quantum Hitchin system. So it's, if you write down these operators, for example, here, then, well, they define a holonomic system. And then this holonomic system has some singularities, because we have you have some things like yi minus yj squared and so on. So if you compute carefully, you will discover that there is a divisor of singularities which has many components, and that's exactly that divisor. And outside, so this is the divisor on which these eigenfunctions are going to have some kind of singularities. But outside that divisor, they're analytic, and they will satisfy for complex field. So this is for so over complex numbers. They will satisfy these differential equations, which is the eigenfunction for the Godin operators and also complex conjugate Godin. And spectrum of Hecke operator embeds into this set of real operators. Actually, we conjecture that they are the same, but what remains to be shown is that every eigenfunction, joint eigenfunction of these Godin operators, which is single valued, actually lies in L2. Because in order to represent an element of the spectrum, it should lie in L2. And it is kind of, we want to say that this is more or less obvious, because the local behavior of eigenfunctions should not depend on this eigenvalue, but we could not make that precise rigorous argument for that. in any case, I expect that we will be.
Sorry, Pasha, very silly question. I guess I should know, but I don't. The characteristic variety of that quantum Gaden system, is that some variety of like something with a nilpotent Higgs, or what's the relation between them?
Yeah, nilpotent cone. It's the hero's fiber of the kitchen.
Okay. And the very stable bundle is the very stable divisor is defined as those bundles that don't have a nilpotent.
They don't have a nilpotent Higgs field which preserves parabolic lines.
Okay.
Okay, and so and also if psi is a joint eigenfunction of this gi and gi bar, which as a distribution, so if gi and gi bar act on it as a distribution on the moduli space, then it lies in HK for some case, then it lies in L2. So we were very, very close to showing that actually sigma equals R. And it can be done for 5 points, so I will explain that. Okay, now Schwartz space. So actually an important role in this whole business is played by Schwartz space, which is, informally speaking, a space of functions with rapidly decaying coefficients with respect to this basis. But of course, you have to say what it means rapidly decaying. So the precise definition is that so this means that if you apply any Hitchin Hamiltonians, so any element of, so it's an element of H, such that if you apply to it any of these Hamiltonians as a distribution, it will remain on this H. So in other words, these Hitchin Hamiltonians have some eigenvalue, and basically if you multiply the coefficients of Fourier coefficients of our function by any product of eigenvalues of these L's, by eigenvalue of any element of our algebra, that sequence will be in L2, even though these eigenvalues of L's can grow polynomially of arbitrary degree. And then the theorem is that, well, maybe this should not be a theorem. This is maybe a definition. And the theorem should be that quantum Hitchin Hamiltonians, part 2, which is quantum Hitchin Hamiltonians are essentially normal on this space. So this means that if I take any of them and add to it complex conjugate, add to it adjoint, this is essentially self-adjoint on this space. So that means that they we can just independently build this spectral decomposition, just starting with one of those sufficiently generic elements, or all of them at the same time of this algebra. So this is some kind of functional analytic technicalities, but anyway, are there any questions?
Keep going.
Okay, now let me explain what happens for 5 points, in which case you can calculate explicitly. So that very nice geometric picture. So you have this Ban 0, which is the blow up so we have this Ban 0, which is a blow up of P2. So we have 5 points, 0, 1, S, T, and infinity. And we have Ban 0, which is blow up of P2 at 5 points, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, and ST1. And so we will, so basically, so that's the exact structure of this Ban 0S. It's a blow up of P2 at 5 generic points. And we will represent points on P2 by coordinates y and z as a yz1. And then the divisor of these non-very stable bundles of singularities of Hitchin system turns out to have 16 components. So you always have a power of 2 of components, namely 2 to the power of, starting from 5 points, it will be 2 to the power number of points minus 1. And so here are the components. So here is the picture that tells you everything. So you have 5 points, which you blew up. So there are these exceptional divisors at those points. There are 5 of them. Then there are lines connecting those points. There are 10 of them. And then there is a quadric going through all those points, which is given by this equation. And so that's so these lines are listed here in this presentation, and then there is this one. And this is a normal crossing divisor. So the lines, of course, don't normally cross, but when you blow things up, they will become normal crossing. There is an action on this whole thing by our symmetry group. In fact, if you also allow to commute the points Ti, then there will be S5 semi-direct product with Z mod 2, 5, 0, which is Weil group of D5. A stabilizer of one component is a Weil group of A4. And what you get is the graph they form. So these are all P1s, and they form a graph which is called the Clebsch graph, which is a 5-dimensional hypercube modular central symmetry. So it's a graph with I think 16 vertices and 40 edges, and very symmetric and so on. Has the symmetry of this group. And the theorem is the following: that basic solutions of the Hitchin system, which is a rank 4 holonomic system in this case, so that behave near the generic point of D, which is like point somewhere here, as well, 3 of them are holomorphic, and the 4th behaves like square root of Z. So here we don't even get logarithmic singularity. Near intersections, they behave like this. 2 are holomorphic, 1 is square root of Z, 1 is square root of W. And so therefore, these single valued eigenfunctions behave like this. So near generic point, they behave like psi 0 plus absolute value of Z times psi 1. And special points where 2 divisors intersect, psi 0 plus absolute value of Z times psi 1 plus psi 2 times absolute value of W, where these things are analytic functions. And so we see that, in fact, they're continuous. So in this case already for 5 points, eigenfunctions are continuous, although they are not differentiable. And the monodromy around the components are as follows. So there is this is monodromy around one, and this is a monodromy around the other at the point where they collide. So monodromies tend to be reflections, which is an interesting observation, I think. And also these, I should say that this function psi 1, for example, isn't arbitrary. So actually this whole thing is a pullback. So you have a map. Suppose you blow up a plane. So you have a map from the blow up a plane to the plane, and then you can pull back a half density from the plane to the blow up of the plane. And that will have a peculiar behavior near the exceptional divisor. And it will have this type of vanishing, but it will otherwise be not arbitrary. So there is more or less this psi 2 is constant along this divisor, and that's what it's going to look like. And so, well, and we expect a similar picture for more than 5 points, but we haven't computed everything yet. There is a slight difference in behavior for odd and even number of points, because for odd number of points, for example, we don't have semi-stable bundles, which are not stable, but for even number, we do. And so what solutions will look like this. So these eigenfunctions near generic point of the divisor, it looks like psi 0 plus absolute value of Z to the m minus 2. This is for odd number of points times psi 1. And psi 0 and psi 1 are smooth. And psi1 is not arbitrary again. There should satisfy some condition of that sort again. But when m is even, then there will be, okay, absolute value of m minus 2 will then be analytic. So that is not a new thing. That could be subsumed into psi 0. But what will be new and what will arise is absolute value of z to the m minus 2 times log of the absolute value of z. And in that case, monodromy is going to be, so in the first case, monodromy is going to look like this, except that the size will be 2 to some power, but there will be many ones and just 1 minus 1. So that would be a reflection. But for even m, it will be a transvection. So it looks like this. So there is a small Jordan block 2 by 2, and the rest is just the identity. So it's a kind of unipotent reflection. That's the form that we get. So any questions up to this point? Questions? Okay, so then let me explain what happens for over real numbers. It's actually fun, and we don't fully understand the picture yet. But we computed what happens for the case when all parabolic points are real. You don't have to assume that. You can take, for example, them in complex conjugate pairs. And so in that case, let me draw my P1. So that's a circle. And here are my points. So I drew the case of 5 points. So T0, T1, T2, T3, and T4, which is infinity. And in this case, okay, so I look at my authors. So this is where my authors live. And so I can look at the monodromy of the authors. So so I'm going to compute monodromies with respect to some, so we have this equation for the eigenvalue, the author equation. And then I can compute monodromy around these things here. And in an appropriate basis, monodromy around this thing is just this kind of quasi-unipotent Jordan block. Because when I go around completely, I get unipotent block with eigenvalue -1. So if I go around halfway, I'm supposed to get square root of that, which is this I01I in an appropriate basis. And then if you go from one point to the other, then again, in an appropriate basis, you will get a matrix which has this form, 1 bj 0 minus aj. Except the last one, where you might need a lambda on the diagonal, but otherwise the same. And then there is a condition that if you go the whole circle, well, inside everything is regular, so the product should be 1. And the matrix here will be minus j, actually. So you will get a product -1. Or you go, so because you can contract it on the upper hemisphere. And similarly, if you replace j with j inverse, then you also get -1 because you can contract to lower hemisphere. And in particular, this means that this lambda should be 1. Not 1, but the product of aj inverses. And so this is a family of equations. So how many unknowns do we have? So we have these a's and b's, and there are m+2 matrices. So we get 2m+4 unknowns. And there are 6 equations because there are 3 matrices with determinant 1, which are equal to minus identity. So we get 2m-1 dimensional space of solutions. And this is actually just a parameterization of the space of flat connections on this manifold. So we have m+2 points. So we have what? We have free group with m+1 generators. And then the product is 1 of those m+2 generators, product is 1, and we mod out by symmetry. So no, sphere, it's a sphere, right? Okay, it's a sphere. So we have m+1 generators, product is 1, so that gives us M matrices, and modular conjugation, so that gives us M-1 matrices essentially. So, and the eigenvalues of those matrices are fixed. So that means each matrix gives you a two-dimensional space. So you will get this kind of space. Sorry. Yeah. So let's do it again. So we have M+2 generators. They are all basically anti-unipotent. So that you get 2 times M+2. The product is -1, which gives 3 equations, and the modular symmetry that cuts out 3 more dimensions. So we will get 2m+4 -6, which is 2m-2. And so this is a parameterization of flat connections. And then the question is, what is the condition to be real order corresponding to eigenvalue of the Hecke-Aperoid? And it turns out that this is the condition of being a balanced connection. So that's a new notion that we introduced. The connection is called balanced if the numbers aj here are equal to 1. And in particular, this means that lambda is 1. So these matrices Bj have diagonal entries 1 and -1. And in this case, one can show that the two matrix equations become equivalent. So this is actually a half-dimensional subvariety, most likely Lagrangian. I haven't checked with respect to the standard Atiyah-Bott structure. So this variety, so let's say we just have this equation on matrices where eigenvalues are 1 and -1, and this is a variety x m-1. So it's a complex variety, but we will consider its real points. And then a theorem that eigenvalues of Hecke operators should correspond to as real balanced connection, to a subset of those. Actually, we cannot prove to all. And the interesting theorem is that these balanced connections correspond to non-vanishing solutions of the T system of level M. So there is this remarkable integrable system, discrete integrable system, which is called T system, also sometimes called Hirota system. And it's a system of equations with respect to a sequence of numbers labeled by 2 indices, I and K. Equation is the following: Ti of k minus 1, Ti of k plus 1 equals to Ti minus 1 of k, Ti plus 1 of k plus 1. This system arises in a zillion different settings. In particular, what we get is solutions which live in a strip. So boundary conditions is 1. So it's 1 here, 1 here, at 0 and I equals 0 and I equal m. And then there is some dynamics here. And the T1 of k equals to those numbers bk, which could determine everything here, because this is the only thing that's left unknown. And then there is a remark that every non-vanishing solution of the T system, so solution which is not 0 anywhere, of level m, which means it lives in this strip, is m plus 2 anti-periodic. So Ti of k plus m plus 2 equals to Tm minus I of k. So if you shift by m plus 2, you get the same thing, except that it is flipped. This strip is flipped. If you shift by twice m plus 2, it's just completely periodic. And actually, this is the homologic of conjecture. It's not so easy to check, actually. And it's the homologic of conjecture, which was checked by Edik Frenkel and Andras Seniš. It is funny that another work of Edik from a very long time ago becomes relevant here. And there is a more general version of this for any root system. This is SL2 version, but for any root system, you have a similar system. And it's that also has this periodicity property. And this was proved by Fomin and Zelevinsky. And this was one of the starting points of the theory of cluster algebras. Okay, so I think this is all I wanted to say. So thank you. And
Oh, okay. So we have ample of time. Do you have to go to teaching, or we can
Well, I
ask all
have
the
to go to
questions?
teaching at 2:35, but
Oh, okay, okay.
need
We
a
have
few
20
minutes to-
minutes for questions. So please, everybody.
well, a little bit less because I need to set up my computer for teaching, but yeah, probably 10 to 15 minutes.
Well, let's see if we have one question.
I have a kind of silly standard questions, which probably answered in Pasha's thesis or something. So basically, in your previous talk, you had the Lamé system with coupling parameter 1/2.
Yes, minus one, yeah.
And is it because, well, I mean, is it because you just working with characters? But is there some kind of version of this story where you work with like vector valued characters and you get like other coupling parameters somehow?
Absolutely, yeah. So there is so what you can do is you can consider, so actually it's not about vector valued character, it's just, there is a twisted version of this analytic geometric Langlands story, Langlands in any setting, where instead, we're working with Bungie, with parabolic structures. So this means that at every parabolic point, we have a kind of P1, in this case, in general, flag variety worth of possible points. And so we have functions on that. But so essentially our, I mean, for any group, this story with genus 0 would be this space Bungie would be just a product of flag varieties at those points modulo diagonal action of the group. So, but instead of functions on flag varieties, you could consider sections of a line bundle. Or more precisely, absolute value of a line bundle. I mean, you can consider arbitrary. So basically, you have Borel subgroup. So what is flag variety? It's a quotient of G mod B, where B is Borel subgroup. And then if you have Borel subgroup over local field, you can take its characters and look, instead of looking at, and this defines an associated bundle with structure group, let's say R plus. So if it's a character into R plus, and then you can just take the corresponding, instead of functions, take twisted functions. And then everything will get twisted. So you will have Hecke operators, so some powers will appear in them. The differential operators will also be twisted. So these Godin operators will also have some parameters in them. So actually, this is a way to introduce M, so you can introduce M plus 2 parameters into this game. At every parabolic point, you can have a parameter for SL2 case. And in particular for the 4-point case, you will get 4 additional parameters. So not only will you get general Lamé equation, but you will get general Hoyne equation. So you will get arbitrary monodromies, not just unipotent ones, but arbitrary monodromies at the functions. And there is a theory which is quite parallel to this. I mean, it's a bit more complicated, but it is otherwise quite parallel. And especially if these twisting parameters are imaginary, then all the analysis goes along for the right also. Or if they are real, but between 0 and -1. Now, if they are real and go beyond 0, -1, then what you will get is a signature of the inner product will not be positive, and there will be analytic complications. But actually, integer values of these parameters are interesting because they are related to classical Godin model on tensor product of finite dimensional representations of SL2. So that's my answer. So, Lyosh, does it answer your question?
Thanks. Yeah, that's a lot of great stuff there. Yes. So.
Wow, such an answer that I forgot my previous question. Now let me try to remember. Here it was. So you had in the previous talk you had your eigenfunctions with a bit of singularity, with logarithmic singularity. Right?
Yes.
What happened today is that if you have enough parabolic points, that in fact your eigenfunctions continues.
Yeah, and
That-
moreover, I think
is that the general expectation?
or maybe in higher genus, yeah, we hope that we hope that they will these singularities are not that bad actually.
No, but there's no singularity, it's just continuous function.
Well, I mean, it's
And
still
in fact, it gets more
differential.
and more derivatives as you increase the number of points, you get more and more derivatives.
That's right. That's my at least in genus 0. That's my hope. At least for genus 0 and the m points in generic point of the divisor. That's what happens. You get absolute value of z to the power m minus 2. So there you can take a certain number of derivatives, which depends on the number of points. I don't know what happens at the intersection, so I don't know actually if this divisor is normal crossing in that case. But I will find out from algebraic geometers. And hopefully that's the picture, yes.
Okay. More questions? Well, if there's no more questions, let's thank Pasha and Edik for this very, very enjoyable and what's the word? What's the word that, for things that contain a lot of information? Information rich sequence.
Informative.
Yeah, informative, exactly. Informative, mini course. So let's all clap.
Thank you, Pasha.
Okay, thank you.
Thanks, everybody.
Bye-bye.